Right, okay, in this video we're going to look at circular motion with a view to then eventually getting on to simple harmonic motion. We'll spend a couple of videos looking at circular motion, and eventually we'll get on to the simple harmonic. Okay, so what is circular motion? So circular motion is anything that moves in a circle, basically. So if we have an object moving in a circle, then it's described as being moving in circular motion. Nice obvious one to suggest for this one is that you could have something on a string moving in a circle, and eventually when we get onto more fields and we look at astronomy, we'll start looking at Newton's laws causing these forces and causing this situation. But for now we'll just deal with simple things on a string going round in a circle, because that makes sense. So what we've got here is there's a lot of different information you need to know about circular motion. So in order to look at circular motion in detail, we need to obviously have a definition of the radian. Now the radian, you may or may not have come up in class with me before, but the radian is basically just another way of measuring angles. So far, probably you've only used up to 360 degrees, and that represents a full circle. In terms of the angle inside. Now, in radians, we deal in pi, basically, where a full circle is 2 pi. And that comes from the relationship because of relating the ratio of the circumference to the size or the radius of the circle. So here we have the radius of the circle, and the circumference of the circle all the way around is 2 pi r. And when we relate those together, if we do 2 pi r over 2 pi, 2 pi r over r, then the r's cancel, and that equals 2 pi. And that effectively tells us that this is 2 pi. So this angle inside here is 2 pi radians. So it's 2 pi radians for a full circle. And then everything else goes on fractions of that in terms of pi. We've done that. You will do those in lesson, and you will have done those in maths as well, in order to get you used to using pi as radian values. So that's where that comes from, and we're going to be utilising that idea quite extensively in this because it makes more sense to utilise pi and radians for these equations. So the first equation I need to make you aware of, now obviously if something's moving in a circle, then it's going to have a speed. And it's going to have a angular velocity. And we represent these two as, really unhelpfully I suppose, v for linear speed. In other specifications, this tends to be called the tangential speed. And we'll talk about why that is later. And then this value coming round here is the angular velocity. So the angular velocity, so omega, angular velocity. So that's this symbol right here. It looks like a small W for the most part, and you will always write it like that anyway, but it's an omega. So we've got angular velocity and we've got linear speed. So how can we calculate each of these? Well, quite nicely, with the circumference being 2 pi r, the linear speed is calculated as 2 pi r over t. 2 pi r being the distance that it would travel, and t being the time it would take to do that. Now, this is slightly different for angular velocity, because angular velocity is 2 pi over t. Now that comes from the fact that we're actually dealing with angles here. Notice that this is actually an angle because look over here, we said that 2 pi is one full rotation. So one full rotation is 2 pi. So we're working out the amount of time taken to do this angle. So it's an angular velocity. So the time taken to do this angle, where this angle is a full 360 degrees, 2 pi, over t, the time period. Please bear in mind that you can use any angle for this as long as you have the right time to go with it. So if you've got theta, an angle in radians, over an amount of time, and if I was to draw that on here, and we say there's our object moving between there and there, and we have an angle theta there, if we know the time taken to get from there to there, we can use this equation as well. More often than not, we don't. We end up using this because we deal with time periods. Now, even more importantly, is what is the relationship between the time period and the frequency? Well, you should know from previous wave studies that the frequency is equal to 1 over the time period. They are reciprocals of one another. So if you look quite carefully here, because of this relationship, it means that we can replace 1 over t, which I can write this out to make it nice and clear. We can replace this 1 over t with 2 pi f. And that is a really nice relationship that we can get there, because that means if we know the frequency of something moving in a circular motion, then we know its angular velocity, or we can calculate its angular velocity. And that's really, really useful. So let's look at just a situation here, just to get your head around what the difference between these two values is. So I'm going to draw on the board two objects moving in an arc, or a circle, in circular motion. So here's the center of a circle, here's the object, and it's moving from there to there in an angle theta. And then I have another object that's slightly further, that's also moving like that. Now, if I was to tell you that they are moving in the same time, in exactly the same time, what would be the difference, if any, between their omegas, we'll call this omega 1 and omega 2, and what would be the difference between their linear speeds, v1 and v2? Have a look at that, have a think. What can you tell me about these values? Well, let's start with the v1 and the v2. v1, v2, is one bigger than the other? Hopefully you'll say yes, because v1 is covering a smaller distance in the same amount of time. So this one isn't moving very fast, whereas this one is moving very fast. It's covering a larger distance in the same amount of time as this one. So effectively here, v2 is going to be greater than v1 in this instance. What about omega? The angular velocity. Well, look very carefully at the equation, 2 pi over t, or theta over t. What's changed and what's not changed? Well, t's the same. Is the angle the same? Yes, it is. It's exactly the same. So effectively here, omega 1 is equal to omega 2. And so we are suggesting here that even objects that move through the same angle in the same time, no matter their distance, they have the same angular velocity, which is a really important distinction to make. So that's clear in your notes as well. So v2 is going to be greater than v1 in this case, and omega 1 is going to be equal to omega 2 in this case because of the nature of angular velocity and the equations that you're going to employ. Really usefully, we can relate the two equations, omega and v, by another equation, which is v is equal to omega r. Because you'll notice that the only difference between these equations is the r. And we're hopefully going to look at that and experiment with that equation in class.